Imagine rewinding the universe's clock, spiraling backward through billions of years of cosmic history. Galaxies shrink to faint smudges, stars wink out, and all the glittering light evaporates. Eventually, you arrive at a time before any stars have ever shone, a deep, black void of cooling hydrogen gas. This cosmic dark age began about 380,000 years after the Big Bang Space.com. The universe was neutral, transparent, and empty of light-making structures. Yet hidden within that darkness, gravity was quietly gathering matter into clumps, seeding the first galaxies. For decades, scientists thought they knew approximately when those clumps ignited. The first stars and galaxies were expected a few 100 million years ago, years after the Big Bang and Wikipedia.org. But what if some galaxies formed much earlier, grew much larger, and matured much faster than this scenario allows? What if our cosmic timeline needs an update? This is not a speculative thought experiment, but a pressing question sparked by the James Webb Space Telescope, JWST. Since it began collecting light in mid-2022, JWST has peered farther back in time than any telescope before it. Its images show brilliant, compact galaxies that seem to have existed a mere 300 to 500 million years after the Big Bang, and they are huge. They glow red with old stars and heavy elements, suggesting they formed and aged rapidly. Some headlines declared that these galaxies shouldn't exist. Others asked if JWST had broken cosmology. Before we rush to rewrite our textbooks, let's travel through time and space to understand where these galaxies fit and what they might be telling us. Dawn after darkness, the cosmic timeline. To appreciate why these discoveries are so surprising, we need to walk through the early epochs of cosmic history. After the Big Bang, the universe expanded and cooled. Around 370,000 to 380,000 years post-Big Bang, electrons and protons combined to form neutral hydrogen atoms. This allowed photons to travel freely, leaving behind the cosmic microwave background. Yet there was nothing to emit fresh light, plunging the cosmos into the dark ages and Wikipedia.org. The only photons were relic radiation and faint 21 centimeter signals from neutral hydrogen. Gravity was busy during this time. Invisible webs of dark matter began pulling ordinary matter into filaments, and halocene.wikipedia.org. Dense gas clouds collapsed, eventually reaching conditions where hydrogen atoms fused into helium and light burst forth. This cosmic dawn likely occurred between about 180 and 700 million years after the Big Bang and Wikipedia.org. The first stars, known as population 3 stars, were thought to be massive and short-lived, blazing bright in ultraviolet. Their intense radiation began to reionize the neutral hydrogen, ending the dark ages. Observations of high redshift quasars in the cosmic microwave background suggest that this reionization was mostly complete by roughly 1 billion years after the Big Bang Space.com. In the traditional narrative, galaxies at these times were expected to be small, chaotic assemblies of gas and young stars. Massive, well-structured galaxies should have taken billions of years to assemble. A new eye on the ancient universe. Enter the James Webb Space Telescope. With its 6.5-meter primary mirror and instruments sensitive to infrared wavelengths up to 28.5 micrometers physics.aps.org, JWST is optimized to see the redshifted light from the earliest stars and galaxies. Light that left galaxies when the universe was a few 100 million years old has stretched to infrared wavelengths by the time it reaches us today. Hubble's vision extended only to about 1.5 micrometers, leaving it blind to much of the early universe. Webb's larger mirror collects more light, enabling it to detect fainter and more distant objects. Its instruments, like NIRCAM and NIRSPEC, can take exquisite images and spectra, revealing chemical compositions and ages. With these capabilities, JWST quickly began delivering breathtaking deep field images. The Cosmic Evolution Early Release Science Survey, SEERS, combined the telescope's imaging and spectroscopy to probe the epoch of reionization. Early analyses found not only the most distant galaxies ever observed, but also a surprising abundance of bright, compact sources. Even more shocking, some of these galaxies appeared to be as massive as the Milky Way, yet existed only 500 to 700 million years after the Big Bang, scientificamerican.com. Their light carried signatures of older, red stars. They were too big, too bright, and too mature, at least according to our models. Little red dots and the mass illusion. The initial reaction within the astronomy community oscillated between awe and skepticism. Could the universe really have assembled such large galaxies so quickly? Sears-93316 was one such object. Preliminary measurements suggested a redshift of 16, implying an age just approximately 250 million years after the Big Bang. That would be extraordinary. However, when astronomers obtained more precise spectra, they found the galaxy's redshift to be about 4.9 physics.aps.org. It wasn't an early giant, after all. This cautionary tale underscores how difficult it is to interpret faint, distant sources, especially when relying on photometric redshifts alone. Other compact sources remained at very high redshifts, but still seemed brighter and more numerous than expected. Researchers dubbed them little red dots. A key clue came from examining their spectra. Some of these objects harbored supermassive black holes. These central black holes can dominate a galaxy's light output as they accrete gas, making the galaxy appear more massive and mature than it actually is. A NASA analysis concluded that many of the brightest early galaxies were less massive than they first appeared once black hole emission was accounted for science.nasa.gov. Subtract the glare of these luminous nuclei and the remaining galaxies fall closer to theoretical expectations, though there still appear to be more of them than predicted. In other words, cosmology wasn't broken by little red dots, but our understanding of how light from early galaxies is generated and interpreted needed refinement. Yet even after correcting for black hole brightness, the early universe still seems to contain an excess of massive galaxies. There are roughly twice as many of these bright sources as standard cosmological simulations predicted science.nasa.gov. This overabundance demands an explanation. Stories of unexpected galaxies. One of JWST's great surprises is the discovery of galaxies with mature properties in unexpected environments. Consider Pearl SDG, a dwarf galaxy located only about 98 million light-years away. Dwarf galaxies are usually bustling with star formation because they are too small to retain their gas for long and are easily stirred by interactions. Yet Pearl's DG appears quiescent. Its stars stopped forming over 1 billion years ago, universetoday.com. JWST's resolution allows astronomers to resolve individual red giant stars within this galaxy, pinpointing its distance and stellar population. The absence of tidal interactions or nearby galaxies suggests some unknown mechanism quenched star formation in this isolated dwarf universe, today.com. This quirky little system challenges our understanding of how galaxies shut off star formation. If such isolated, dormant dwarfs exist locally, perhaps similar mechanisms operated in the early universe. Another intriguing case is JD's GSZ-140, a galaxy observed when the universe was less than 300 million years old. JWST spectra revealed the presence of oxygen, indicating that multiple generations of stars had lived and died, physics.mit.edu. Heavy elements like oxygen are forged in the hearts of massive stars and dispersed by supernovae. For such elements to appear so early, star formation must have begun very soon after the Big Bang. JD's GSZ-140 is bright and extended. Its existence suggests that galaxy formation began earlier and progressed faster than previously thought. Stories like these fuel the sense of discovery and the sense of tension with theory. Why were early galaxies so bright? If supermassive black holes don't fully explain the brightness and abundance of early galaxies, what could? Astrophysicists have proposed several hypotheses. More massive early stars. Simulations suggest that the first stars may have been much more massive than stars forming today. Massive stars burn hotter and emit more ultraviolet light. When that light is redshifted into the infrared, it makes galaxies appear brighter, physics.aps.org. If early galaxies were dominated by, say, stars tens or hundreds of times the mass of our Sun, they could produce large amounts of light without requiring so many stars or so much mass. Bursty star formation. Star formation may have occurred in violent bursts rather than a steady drizzle. In this scenario, gas collapses and ignites in a starburst, forming stars at rates 10 times higher than average. Such bursts typically last only approximately 100 million years, but they could temporarily brighten galaxies dramatically. Physics.aps.org. Because we see these galaxies at random times, we might be catching many of them during their luminous peaks. Higher star formation efficiency. The gas in the early universe was denser and cooler, enabling it to collapse more efficiently into stars. Most present-day galaxies convert only a few % of their gas into stars at any given time. If early galaxies achieved efficiencies of 50 to 80%, they would have built up mass quickly. Physics.aps.org. Simulations that increase star formation efficiency in this way reproduce JWST's observations, but create another puzzle. Such vigorous star formation should generate lots of dust. However, many high redshift galaxies appear dust-poor. Researchers have proposed that intense radiation and winds from massive stars could blow away dust. Physics.aps.org, reconciling the bright, dustless appearance. Exotic physics, early dark energy, and beyond. Some cosmologists have speculated that the universe may have contained an extra form of energy that briefly accelerated cosmic expansion. Early dark energy models enhance density fluctuations, leading to the rapid formation of massive dark matter halos. Physics.mit.edu. These halos could spawn large, bright galaxies sooner than in the standard model. If early dark energy was present for only a short epoch, it might help explain both the Hubble tension, the discrepancy between different measurements of the universe's expansion rate, and the abundance of bright, ancient galaxies. Other proposed ideas include modifications to gravity, exotic particle physics, or different properties of dark matter. While these suggestions are fascinating, they remain speculative. Most astrophysicists caution against declaring the standard cosmological model broken until all astrophysical explanations, like stellar populations, black hole growth, and gas dynamics, are thoroughly explored. How JWST's discoveries reshape our picture. So, is cosmology broken? The answer is less dramatic than some headlines imply. Rather than shattering our models, JWST is refining them. Astronomers now know that. Early galaxies can be brighter and more numerous than previously predicted. Physics.aps.org. Some of the apparent mass comes from accreting black holes, creating little red dots that exaggerate galaxy sizes. Science.nasa.gov. Star formation in the early universe may have been more efficient, more bursty, or involved more massive stars. Physics.aps.org. A few galaxies, like Pearl's DG, defy expectations by shutting down star formation. earlyuniversetoday.com, showing that quenching processes can operate in unexpected ways. Heavy elements found in very young galaxies demonstrate that stellar evolution happened rapidly. Physics.mit.edu. These revelations do not invalidate the Big Bang, the presence of dark matter, or the broad framework of cosmic evolution. Instead, they illuminate previously uncharted details of star formation, feedback, and the growth of structure. They also remind us that astrophysical modeling is an ongoing process. When new observations reveal gaps, theorists adjust their models. When predictions conflict with data, we revise our understanding. This iterative dance is a feature, not a bug, of science. A humbling perspective. The story of galaxies that shouldn't exist is ultimately a story of curiosity. It highlights the value of asking provocative questions and being prepared for surprises. It shows how even a single telescope can transform our view of the cosmos by giving us a new window on time. JWST's infrared eyes peer through dust, time, and space, letting us witness the dawn of starlight. Every bright, ancient dot on its images is a messenger from a time when the universe was young. Some messages confirm what we expected, others hint at new physics or new astrophysics. Think of the sky on a clear night. Each star you see is part of a galaxy billions of years old. Now imagine a time when galaxies were just forming, when the light from their first stars was piercing the fog of neutral hydrogen. JWST is capturing those moments. Its observations compel us to revisit our theories and ask deeper questions. Why did some galaxies form so quickly? How did the first black holes grow? What role did dark matter and dark energy play in shaping the cosmos? In the end, the question, is cosmology broken, might be the wrong one. Instead, we should ask, What new chapters of cosmic history are we about to write? The universe is not a fixed textbook, but a story we are still learning to read. JWST's early findings show that the narrative is richer and more surprising than we imagined. Rather than being broken, our cosmology is being updated, and with every observation, we gain a deeper appreciation of the forces and phenomena that shaped everything we see today. As more data pour in, future missions will probe even further back, perhaps glimpsing the first population of stars or the seeds of the first galaxies. Each discovery will refine our theories, challenge our assumptions, and remind us of the profound mystery at the heart of existence. The cosmos may surprise us, but it never fails to inspire.